Alpha-BHC wasn't even effective at killing pests, yet it was spread across farmland around the world, and decades later it was discovered in the Arctic. Persistent, chemically stable, and environmentally mobile, it carried properties that would later make it a global problem. Within just a few decades, massive quantities were produced and dispersed through agricultural use. So the question is, if it wasn't the insecticide farmers actually wanted, why was it spread so widely? How did it travel thousands of miles from croplands to the Arctic? And what did it leave behind in soil, water, wildlife, and us? In 1825, British chemist Michael Faraday conducted an experiment in which he reacted chlorine gas with benzene. He was not trying to invent a pesticide, he was studying chemical reactions. The reaction produced a white crystalline compound. At the time, it was believed to be benzene hexachloride because scientists thought chlorine had attached directly to a benzene ring. But analytical chemistry in the 1800s was limited. What Faraday had actually created was a different structure entirely, hexachlorocyclohexane, a saturated ring with 6 chlorine atoms attached. For decades, the compound was referred to as benzene hexachloride, BHC, but once its true cyclohexane structure was understood, scientists corrected the name to hexachlorocyclohexane, HCH. What we call alpha-BHC today is therefore more accurately known as alpha-HCH. That compound exists in several three-dimensional forms known as isomers. Among them are alpha, beta, gamma, and delta. One of those isomers, hexachlorocyclohexane in its alpha configuration, would later become environmentally significant, but for nearly a century, the compound had no major practical use. In 1912, scientists discovered that one specific isomer, the gamma form, had powerful insecticidal properties. That gamma isomer was later marketed as lindane. This discovery transformed hexachlorocyclohexane from a laboratory curiosity into an agricultural product. By the 1940s, during and after World War II, production scaled rapidly. Farmers around the world began applying what was sold as technical BHC to crops, seeds, soil, and even for public health mosquito control. But technical BHC was not pure lindane. When the compound was manufactured industrially, the reaction produced a mixture. Typically, 55 to 80% of that mixture was alpha-HCH. Only about 10 to 15% was the gamma isomer that actually killed insects efficiently. This means that when farmers sprayed BHC on their fields, most of what they were applying was alpha-HCH, not the intended active insecticide. All HCH isomers affect the nervous systems of insects by interfering with GABA-regulated chloride channels, which disrupt nerve signaling and lead to overstimulation and death. However, the gamma isomer fits these receptor sites much more effectively. As purification techniques improved, companies began isolating gamma HCH and selling it separately as lindane. That is when alpha-HCH became something else: waste. To produce 1 ton of lindane, manufacturers had to process several tons of technical HCH mixture. The unwanted alpha, beta, and other isomers were left behind. For every ton of lindane purified, 6 to 10 tons of byproduct remained. Large stockpiles accumulated near factories in Europe, Asia, and North America. Disposal methods were often inadequate. Waste was buried, dumped, or stored in open pits. In some cases, contaminated soil spread beyond factory grounds. At the same time, alpha-HCH that had already been applied to agricultural fields began revealing another property: persistence. It binds to soil organic matter, especially carbon-rich fractions, and degrades slowly. It is semi-volatile, meaning it can evaporate under warm conditions and re-enter the atmosphere through a process known as global distillation, or the grasshopper effect. Alpha-HCH evaporated from warmer agricultural regions, traveled through air currents, and condensed in colder climates. Over time, it was detected in Arctic seawater, snow, sediments, and marine mammals. It had reached places where it was never used. Unlike dramatic poisoning events, alpha-HCH's impact was slow and systemic. It bioaccumulates in fat tissue. It has been detected in human adipose tissue and breast milk in populations exposed through food chains. In wildlife, it can contribute to endocrine disruption and immune stress, especially when combined with other persistent pollutants like PCBs and DDT residues. It was not always the most toxic isomer. Beta-HCH is actually more persistent in soil and body fat. Gamma-HCH was more insecticidal, but alpha was produced in the largest quantities and had the right balance of persistence and mobility to become globally distributed. By the 1980s and 1990s, scientific consensus had shifted. The environmental and health concerns surrounding HCH isomers led many countries to ban technical HCH mixtures. In 2009, Alpha-HCH was listed for elimination under the Stockholm Convention on Persistent Organic Pollutants. Today, Alpha-HCH is no longer produced intentionally in most of the world. However, residues remain in soils, sediments, and former industrial sites. In cold environments, climate change may even remobilize previously trapped pollutants as ice melts and temperatures rise. The story of Alpha-HCH is not one of a single catastrophic event. It is a story of scale. A compound discovered in a 19th century laboratory became a 20th century agricultural tool and then a global environmental byproduct. It was never the star ingredient. It was the leftover. Yet, because of its chemistry, its persistence, its volatility, and its ability to bind to life's carbon systems, it traveled farther than anyone intended. Unlike persistent chemicals such as alpha-hexachlorocyclohexane, which spread through soil and water for decades, remediation today focuses on reduction. Independent lab testing showed drops of balance reduced alpha-HCH in contaminated water by over 80% under controlled conditions. In a separate greenhouse field study, plants grown in pre-treated soil and irrigated with treated water showed significantly lower pesticide levels compared to untreated controls. These results suggest that reducing contamination in water and soil may help reduce plant uptake, supporting cleaner crops and cleaner water. Try Drops of Balance today. Use code SAFECLEANWATER for 10% off.